The concepts of testing and analysis. Testing refers to when you have something that you've made or you're familiar with, and you want to make sure it works in the way you want it. Basically, you have a known state you want to reach, and you just test to make sure it's reaching it. Analysis is when you don't know that. You have an unknown signal, unknown operation, you don't know how a part works, and you want to figure it out. So it's the same thing from two different directions. I'm about to do analysis of the audio ports on devices like computers and cell phones. There is information about this all over the internet that I have just tried to Google and have pieced it together a little bit. But there's no easily available information that I can find all in one nice place for hobbyists like me who want to interface with computing hardware with audio ports. It's probably all in some technical manual and looking at patents and all this other nonsense that somebody in an actual engineering field would have immediate access to or learn in school. But I'm not an engineer and I'm not going to be one. But I still want to do engineer things. So it looks like we're working on breadcrumbs and following up from there. So before I get into that, I want to point out some very simple concepts for safety in analyzing these things. Not safety for the human. That's easy. You know how to not electrocute yourself. I'm talking about safety for the device. How do we probe the internals of a device that we know very little about, especially if it's an expensive device like my multiple hundreds of dollars laptop that I don't want to screw up? How do we do that safely? I'm going to briefly talk about a multimeter first. That's the testing tool. And then we'll get to the oscilloscope, which is the actual analysis tool. You can't use a multimeter for most of analysis because it's not good for anything that's not a steady state signal. It's great for measuring a DC level. It's great for checking out a board to see which part is shorted or broken or whatever, and to be able to fix it. And it's great for checking your power rails and such, but it just doesn't update fast enough to measure a signal. I want to analyze a signal, but a multimeter has 3 modes, at least a common one. There's additional modes like diode test and capacitance and stuff, but the primary ones, the ones that are most important to everyday use, are measuring voltage, current, and resistance, or ohms, if you prefer. And we can generally categorize these as safe, fuse, and off. The basic concept of a voltmeter, which is what an oscilloscope is. An oscilloscope is just the voltmeter mode really fast. But a voltmeter is a very high resistance, high impedance, however you want to look at it, and it measures a voltage drop across itself. It's designed to work in parallel. So you have a load, a component, whatever, and you put it in parallel. And if you recall, your formula, 1 over R total equals 1 over R1 plus 1 over R2. And this is why you can just take an active circuit and stick a voltmeter across a component and it doesn't really affect the operation of that circuit. Because if we have just the component, if we have not added the multimeter, or the voltmeter rather, then you can see that we've just taken the reciprocal, we haven't changed anything. But R2, the resistance here is very, very large, mega ohms. So 1 over R2 is very small. So we're adding a small number to another number, which is not changing this number by much. So to an approximation, we're not changing the resistance. So we get to measure without affecting the circuit. And again, this is what an oscilloscope probe does. You can have, on mine, 1 mega ohm or 10 mega ohms. There are 100 mega ohms as well. But that's how you can analyze a live circuit. So I say a voltmeter is safe because it's a passive, first of all. It's not doing anything. It's not a voltage source. So you can't fry anything. There's no power there. If you connect it to something that's off, nothing happens at all. And it's safe because it has a very large resistance. So whatever voltage is going through it, as long as it's not a lightning bolt, it's going to drastically limit the current, the power, to make sure that whatever voltage the other thing is putting out, it doesn't fry. So I can, if I want to analyze the speaker port of my computer, plug a voltmeter right into that speaker port. And I might get no signal or no measurable signal if that high impedance ends up being a problem, and then I can turn the impedance down, use other methods. But as a first thing, just to see what happens, it's safe. Because at worst, you get a trickle. The amp meter is limited by a fuse, and I actually blew a fuse on my multimeter just measuring a battery, a 9-volt battery. The amp meter is another passive sensor, but this one has very little impedance, almost none. Basically, it just measures the current going through it. You stick it in series with the circuit. So you again do it with a live circuit, but make sure that you know what you're measuring before you measure it. Don't just try to measure how many amps a battery can put out, because the answer is enough. And resistance has to be done with the device off. This is the active scan. Your multimeter will generate a current. It generates a voltage, which generates a current. Now, it's a small one. It's not going to be a lot because you have to be able to use a multimeter with different things that are very delicate. But just to be aware, it is a non-zero voltage, so I don't want to just stick that in my audio port. It should be fine. Again, it's a small voltage, but just in case it's not, this is the dangerous one, quote-unquote dangerous. It's the only active scan. But just like here, what if that port is generating a voltage? And it is, it's a signal. So right now, I don't know what impedance the port of a computer expects. If I plug the amp meter to see how much current is going through, I might fry the circuit because it might be expecting anything you plug in there will limit the current. So that's why I've labeled voltmeter safe, because it's passive and it has a resistance. Amp meter is passive but very little resistance, and this one is active. So going back to our oscilloscope, the oscilloscope is a fancy voltmeter, which means it's safe. So you can put an oscilloscope wherever you want, and the worst that happens is it didn't work, and you have to figure out a different way to measure it. So easy enough, we know how these tools work. So what are the three dangerous things? As a reminder of our equations, voltage equals current times resistance, power equals voltage times current. Ohm's law and Joule's law. So what do we have? Voltage, current, and power. These are the three dangerous things. And you might say they're all the same thing. It's electrons moving in a wire, since we're only talking about wired electricity, not any other type of electricity. It's just electrons moving. But these three things talk about how the electrons are moving, how many of them are moving, with what force they're moving, and what the effect of them moving causes. And since we're talking about danger, what's important is how they're dangerous. Voltage is dangerous to parts. Current is dangerous to people. And power, just to break the symmetry, is dangerous because of heat. These are the core concepts. So if you've ever overclocked something like a CPU in a computer, overclocking means you run it faster than it's supposed to go. But if you run it too fast, then it becomes unstable. It's perfectly safe, it just doesn't work. But to make it work better at a faster rate of operation, you increase the voltage. This generates more heat because increasing the voltage increases the power. That's heat. So you have to cool it better. And then you get liquid cooling, liquid nitrogen cooling, all this other stuff. But there comes a point, even if you had perfect cooling, even if you could rip the heat out of there the second it's made, the instant it's made, if you increase the voltage too high, you'll break it. If you look at spec sheets for things like transistors, it lists a maximum voltage, in fact, multiple maximum voltages for different directions, different junctions, in addition to the power dissipation. Power dissipation is the heat, but it also lists the voltages that can be sustained. If you look at a resistor, it doesn't. A resistor will only list the power rating because it's only about heat. You can put as much voltage as you want across a resistor, as long as the resistor is high enough so that the current is limited so it doesn't catch fire. But a transistor, even if you have very low current going through the thing, if you apply too much voltage, it will break. That's why I say voltage is dangerous to parts. And you say, no matter what, if you limit the current, limit the power, limit the heat, it'll be safe, right? No. That's why it's important that the oscilloscope, the voltmeter, is a passive thing. We can trust the device to generate only a voltage it can handle. Whatever voltage we put in there, we had better be sure, start low, turn it up until we get the operation we want. But we don't want to introduce just any voltage, even if we drastically limit the current, because high voltages can break parts. Current is dangerous to people. If you look at a chart of how much electricity is lethal, there's like a little vertical chart I've seen, they list it in terms of current and voltage is not mentioned. Now, of course, this leads people to say things like, it's not the volts that kill you, it's the amps. If you say that, you're an idiot. Don't say that. Voltage with resistance causes current. It's right there! It's right there! The human body has very high resistance, which is why I can just touch a battery, which is why I can just touch the ends of my bench power supply if it's on a low voltage. But if my hands are wet, it conducts better, less resistance. People put batteries on their tongues to get a little tingle because it conducts better. There's all kinds of electrolytes in there that love to conduct. Now, current is, of course, dangerous to parts as well. You'll see maximum current ratings, but it's much more dangerous to people because generally when you're working with parts, you're controlling the voltage and current is the side effect, really. So if you're doing your voltages right, you're not going to go above the current limit. So it is a concern, but unless you're using incredibly weak parts, you'll generally run through the voltage limit first. So the current is more of a people thing, but it is dangerous to parts. And then, of course, power is heat. Power is when something is working perfectly fine. It can handle the voltage, it can handle the current, it can handle everything just fine, but it's too hot. And the heat breaks it. It's just a different mechanism. Like I said, a resistor, all you care about is the power, not the volts or current. So these are the things we have to limit. The oscilloscope probe does not generate a voltage, so we don't have to worry about that. The oscilloscope probe has impedance, resistance, so we don't have to worry about this. If we just plug it into the port, the only voltage is created by the thing, and that should be safe. The only current is generated by the thing. We're not introducing current, and furthermore, if it's expecting an impedance, an oscilloscope will be plenty of impedance. So if we get a spike, we know we got to be careful turning it down. If we get nothing, then we say, oh, we have way too much resistance. This thing is expecting a very low resistance. And we can just turn it down by adding resistors in parallel with the oscilloscope probe. For example, 10 mega ohm oscilloscope probe. Add a 10 mega ohm resistor in parallel with it. Now it's effectively a 5 mega ohm resistance. For example, we can bring it down gently that way. And heat, for an oscilloscope, that's no problem because we're already limiting both voltage and current. Oh, look, we're limiting power. So this was just a quick review of basically the super safe, ultra conservative baseline, a passive scan that resists whatever is being done to it. Basically, you just peek in the door. You just take a look through the peephole. And then you can get further and further and further. You can start applying a very small voltage and turn it up. You can start applying lower resistance to try and get whatever current the thing is generating to increase. Or if it's not generating current, you can start generating current yourself slowly. But we start from zero and the power follows. So that's how you poke and prod something unknown but expensive so that you can still keep the thing at the end. And very soon I'll have a demonstration of that as I start poking and prodding my very expensive laptop. So until then, I'll be seeing you.